Hey everybody, in this video I'm going to show and explain a simple program that copies a file using system calls in an x86-64 YASM Assembly program. We're going to use the system calls to open an input file and read characters from it. We're going to use another system call to create a destination file and write characters to it. And we're going to use a looping buffer, which should be kind of fun in the middle. And I'm just going to do my best to explain as much as I can. I should say, though, that before you can watch this video, you probably already need to know how to program in assembly, at least in a basic level, YASM Assembly. And so if you don't know how to do that yet, this video is probably going to be confusing for you. You probably need to look at my other videos dealing with YASM Assembly and system calls and so forth. So I'm just going to show you real fast what's actually going on in this source file so far. So this is my assembly program. It's not finished. I'm going to write it on screen for you for the most part. You can see I've got a data section here, and then I just have a bunch of null terminated strings. So I've got a string saying, hey, the module started, we're about to open the file, we're about to create the file, we failed to do something, we're done copying, we terminated the program, whatever, right? So I just have some strings, no big deal. Down here, I have something called the copy buffer length, which is just the size of the buffer that I'm going to use between the input file and the output file. So a 2-byte buffer is really inefficient, it's too small, but I made it 2 bytes just to show to you that our looping read area is going to actually work. Because if I make a buffer that's too big, if it's bigger than the file, then we won't actually know if the buffer loop works or not. So I'm just going to put 2 here. Could change that later if we wanted to. We're going to be reading from a file called input and writing to a file called output, so that's no big deal. In order to open a file with the system call for read mode, we're just going to use a 0 as the flag, so that just means read mode. And then for the creation of the file, we're going to use some standard permissions. This is not a permissions video. I'm going to probably release a permissions video at some later point in time. Not too important right now, but basically this 640 is the heart of what permissions we're actually looking at. Q is quad word. And 6 just means that the owner can read and write to the file. 4 means that anyone who is in the same group as the file has been assigned to, which is usually the owner, can just read it but not write to it. And then everybody else, people who are not the owner and who are not in the right group, they have no access to it. Just a simple security feature of Linux for file permissions. You can go a lot further than this in the terminal, but for this assembly program, we're just going to use basics. We're not going to use ACLs. I don't even know how to do that in assembly. System call codes. So again, if you don't understand system calls, you got to watch my other videos first. But we have a code of 0 to read from a file, 1 to write to a file, 2 to open a file, 3 to close an opened file. Probably should have put that one before create, but I don't really care. 85 is the code to create a file for writing, and then 60 is the code to exit from the program. So then we have file descriptors. Descriptor number 1 is standard output. Descriptor number 2 is standard error, and it's always 1 and 2 no matter what program you're dealing with. Unless you have some kind of really crazy non-standard thing going on. And then for the exit codes, we're just going to say exit 0 for success and exit 1 for failure. Now to the actual text section where our instructions are in the assembly program. So you can see section text here. We've got a global entry point called _start. So this is not a GCC program that requires a main entry point. This is a pure assembly program that requires an _start entry point. Again, see my other videos for more assembly explanation. I'm going to call on a method, well, not a method, a regular function called welcome, just to print a little welcome message. You can see right here, that's all that's doing. It's just loading, a string, sending it to standard output, and calling on a helper function that I made called print null terminated string. When it's done with that, it just uses the call code to exit the program. No big deal, nothing too advanced so far. I have the tests function commented out because I want to write that in front of you. And if you look at what I have inside of print null terminated string, this is not the point of the video, so I'm just going to skim it. It's not super important. But, I want a function called print null terminated string that takes in a pointer to a character array and a file handle for where you want to print it. And what it'll do is it'll come in, grab the incoming arguments. It's only got 2 arguments. So it uses R12 and R13 to store those arguments, and then R14 is the result of calling another helper called string length. You can imagine my string length function just kind of scans the string until it finds a null terminator, aka the number 0, not the ASCII code for 0, but actually a 0, in order to figure out how long the string is, and then it can use a regular system call to print the string to the right file descriptor. So we're going to be doing mostly this, kind of this exact same thing when we copy the file, so I'm just definitely not going to explain it. If you don't know pushes and pops and epilogues and prologues, see my other videos. CRLF is just going to print a carriage return new line, carriage return line feed, so that's just like making the cursor go to the next line. Not a big deal. We just print a string basically. And then I have a custom die function that allows us to die with a failure code of 1. Oh, I forgot to mark that. Let's see, 206 exit fail. I'm just going to put that down here. Yeah, instead of hard coding values, it's a lot better to use variables if you can, or defines. So all it's going to do is just kind of print an error message and then exit with the, the appropriate exit code, which is just going to be 1 because this is a simple program. So CRLF, print null terminated string, dying, string length, a welcome message, all this fun, pretty stuff that doesn't really do anything except make the program more fun to look at. So I'm going to run it here and make sure that it actually works. Okay, nice. Okay, so if I run it, you can see that the makefile system, again, this is not a makefile video, so I'm not going to show you my makefile. See my other videos if you want to learn more about makefiles, but you can see that the assembly program says that it started and then it just exited. Then the makefile continues to run these extra commands that I have set up. So this is not part of the assembly program. This is just taking a checksum, an MD5 checksum of the input file, and then an MD5 checksum of the output file. If you don't understand what MD5 checksums are, I'll probably release a video sometime in the future if you're interested on all my platforms, just talking about why you would use a checksum. But for now, just imagine this is a fingerprint. So if the fingerprints don't match, that means the files don't match. Right now, the output file doesn't even exist, so it just is an error. And that's why the makefile thinks there's an error, because the output file didn't exist. So that's the basics of kind of getting started with this, bare bones program. Now let's start looking at running the file tests. So file tests, we got to make a new method. I'm going to stick it down here. Let's see. I got a solution up so that I don't have to spend too much time typing. I'm going to try my best to balance between copy pasting and just typing very quickly. But let's see, where's the file test? So we got this. I'm going to put the signature up here real fast. And you know what? I'm feeling pretty lazy. I'm just going to copy paste the whole thing. Copy paste the whole thing. So now this method right here is going to get called the file tests. So I keep saying method because I teach C++ a lot too. File tests, if we go down further, this function is called file tests. Here's the signature. It doesn't take any arguments. It just kind of does stuff. It doesn't return anything. And here are the registers that I'm going to use. I'm going to have the input file handle, the output file handle, and then the count of bytes read from the input file at any given time inside of our looping buffer reader section. So the first thing I've got to do is I've got to open a file to read. The second thing I've got to do is create a file to write. And then I'm going to copy the input file to the output file. And then I'm going to print a message saying, hey, everything was successful. And then I'm going to close both files. Notice how I'm not actually doing anything. I'm just sort of calling other functions to do the work for me. Again, if you don't know the prologue and epilogue stuff or calling functions and returning, you should see my other videos. But I just like to use helper functions. Assembly is like so unwieldy, right? It just gets out of control so quick and so confusing so fast. So anytime you can just, take a chunk out of your assembly code and move it somewhere to another module or to another function, it's probably going to make your life a lot easier and make debugging a lot easier. People who try to write the entire portion of their program in just one gigantic function, those are the people who usually end up spending 10 times longer debugging for no reason at all. So I believe in the power of modular thinking. So anyway, what are we going to do inside of the open file read function? It's not too bad, to be honest. Let's see if I can find it real quick. Open file read. I'm going to copy paste it because, again, I'm pretty lazy. I'll just explain what it is though. So down here, we need a function called openFileRead. So I'm just going to do that. And you can see the signature that I've chosen for this is, I like to write all my functions in C++, kind of lingo or prototypes, so that I can have a better understanding of what the assembly is actually supposed to do. So you can see the function called openFileRead, I want it to take 2 arguments. The first argument should be a pointer to a string that represents the file name that I want to open. And it should be null terminated. Again, if you look back at my strings up here, they all have little zeros at the end. So they are all null terminated. Anyway, so that's the first argument. That's going to show up as RDI in assembly. And then the second argument is the flags for opening the file. So I think probably that was redundant. If I name this openFileRead, then I think it should be obvious that the flags are just going to be the read flags only. So I probably didn't even need to provide this. That was bad design on my part. You could write a better one on your own where it's just 1 argument. And if the name is read, then just use the read flags. But maybe if you want to leave the flags in there, you could just say open file only. It's up to you. Anyway, so it attempts to open a file for reading. If it is successful, it'll return the file handle. That's the long return type right here, long file handle. If it fails, then it will just basically complain and exit the program. You probably want a more sophisticated way of handling errors in your program. I just decided to complain and exit the entire program because this is, not supposed to be super complicated. I just want to show you how to copy files. And then for me, I like to leave comments that just sort of explain what I'm using the registers for. And once my functions get so complicated that I actually run out of registers, then that tells me I probably need to just make another function, split the work up in some way. So far, so good. I only end up reusing the same registers for multiple purposes occasionally. I'm not a hardcore assembly programmer. I'm just, I'm like medium. So I'm going to use R12 and 13 and 14. That's why we have the prologue pushing all those registers to preserve them because they're callee saved. And then the epilogue that just kind of pops them. I've got a label here for the function. Remember, a function is just a label and then a return statement. And as long as you obey and respect the ABI, like preserving certain registers, then you should be okay. First thing I'm going to do is grab the incoming arguments. So I'm going to grab the file name, which is a pointer, which means it's just a 64-bit integer. I can stick that into a register, and then the flags, same thing. So I'm going to grab RDI and RSI, the incoming arguments. I'm going to stick them into R12 and R13, so the character pointer and the flags. And then I'm going to attempt to open the file with a system call. So system call is right there, line 168. If you look up the table for system calls in my favorite book that I usually recommend, or any table that knows the system call codes for x86-64 assembly, then it'll say, well, the system call code to open a file is some number. I've assigned that to SYS open. If we look up here, open is code 2. So that's why I don't want to remember the numbers. It's bad to hard code numbers, so I just put it as a define. And then the first argument that it wants in RDI is the name of the file, so I just gave it R12. I guess I probably could have just used RDI directly in the system call, but that tends to make me nervous. Reusing the argument registers, I like to have them somewhere where they're not going to be destroyed. If I, let's say I accidentally, added some code here on line 163. If I wanted to reuse RDI and I accidentally added some code there, then RDI would have been destroyed. Would have cost me a bunch of time debugging my program. Although I admit it's not super efficient to do it that way. Then we're going to do the file status flags as the second argument, and then we just do a system call right away. So the RAX register gives you the result of your system call. Notice how we use RAX to send in the call code, and then the system call sends us back its return result also in the RAX register. So I'm just going to save that right away to R14. You can see up here, it's just the file handle. So we can assume maybe at this point that we have a file handle sitting in R14. What is a file handle? When you ask the system to open a file for you, the operating system under the hood is just going to do a bunch of stuff to actually open a file. It's going to take the string that you sent it, and it's going to parse it and figure out, how do I interpret where that actually is on disk? I'm going to look at like the file system and the paths that you provided. I'm going to look at the mount points, and I'm going to figure out like, where exactly on disk does that file start, and then the operating system stores that. The operating system stores the file name, it stores where you're looking at the file currently, stores a bunch of stuff that you don't want to have to remember. It creates data structures under the hood. And all it'll give you back in return is a file handle for simplicity, because then later you can use that file handle to just sort of say, I would like to write some bytes to a file, or I would like to read some bytes from an open file. Here's the handle you gave me previously, and then it'll just work, assuming you have a valid handle. So the handle is kind of the most important part. We need to check to make sure that it actually succeeded or failed, because it's a mistake. I've said this in other videos. It's a mistake that new programmers make, or lazy programmers make. Let's suppose, for the sake of argument, file open syscall. Pretend we're in C++, and there is some sort of an API function that we can call either directly to the system or some person's library, and it'll open a file for us. So maybe like a string path, and then forget about the flags. Let's just say we call this, right? So I'm going to do like a little comment. If inside of your program you just call it with some path, and then you assume that what you have is a valid handle. If you assume that what you got back is a valid handle, or maybe this is not a function that opens a file, maybe it does something else. If you just assume that the call succeeded, your program is probably going to have errors when you least expect it, and it's not going to look good, especially if you release a function like this to the public, or if you have like a professor who's like grading your code, and they are testing to see if you're checking for return codes and stuff like that. That's not a smart idea, right? Like, you shouldn't proceed as if everything went according to plan. What? I'm just proceeding as if everything went according to plan. You want to use an if statement, right? You want to say, if the handle has some value that seems to be valid, like for example, more than 0 in the case of opening a file, I would say probably more than 2, because all of our programs always have automatically assigned file handles of 0, end 1, end 2 to represent standard input, standard output, and standard error. But I think usually people just say, like, if it's greater than 0, then it's fine. For me, I might put greater than 2, but more than 0 is fine. The point is, check to make sure that it actually succeeded. Do I have spell check on this thing? Oh God. You're all going to see my true spelling. Let me see if I can get it on real fast. Plugins, what? How come this? Oh, okay, now it's highlighted. Okay. So if it looks like it succeeded based on some kind of a comparison of the return result, then we'll proceed in one way. Otherwise, we'll respond to the error by, doing something else somehow, like writing a log file, sending an email, complaining to the user, doing any number of things where you can actually respond to the error. Maybe you probably want to change your execution path. Like, if the file successfully opened, then go ahead and start writing to it or reading from it or whatever. But if the file did not successfully open, then you probably want to do something else in the program and not just start trying to read from the file. So anyway, super, super good idea. And so that's why I'm going to implement that inside of assembly too. So instead of just immediately using the file handle, I'm going to check it. And I'm going to say, let's compare it to the number 0. If we succeeded, then let's go to another label called read success. I personally, when I'm doing branching logic, I like to say open file read is the name of the function, and then I'll just append some kind of a suffix to the original function name. That way it's easier to avoid collisions when you have lots of functions and lots of labels and things like that. So I'm basically saying if we succeeded, I'm going to jump to this label, which is down here. And so this video also is not about branching logic and how to implement those instructions. You can probably infer it by looking at my code, but see another video in the future for that topic. Anyway, if we succeeded in opening the file handle, then we're just going to say, oh, we were successful, and then we're going to let's see, we're going to print the name of the file that we just successfully opened, and then we're going to send the file handle into RAX so that this function has a return value of long file handle. So when you open a file to read successfully, the caller will receive the file handle. And you might be wondering to yourself, wait a minute. It just gave us the file handle in RAX. Remember, we got to respect the ABI. Anytime we jump anywhere or call another function or call another syscall, which a lot of these things do, we will probably lose the value of registers that are not callee preserved. And that's definitely RAX. I mean, just doing any system call like this print null terminated string function does, that's going to destroy RAX. So that's why I saved it away first in R14. Then at the very end of the function, right before I return, I'm just going to grab R14 and send it into RAX. Again, respect the ABI. Do not return data as a return value in R14 or any other register. You have to use the designated registers. And in this case, an integer that you're returning from a function call is always going to be RAX. Anyway, so that's the gist of that. Let me go back up for a second. So notice how we're sort of comparing. Oh gosh, I just reconfigured my annotator and I bought a new draw pad. I wonder if this is going to work. It works. There's a bunch of stuff I added too. So notice how we try to open the file and then we sort of compare the file handle to see if we actually succeeded or not. If it succeeds, it branches off to the success area down here. Oh, my green's not working. Oh, it's tricky. I got to hit it in a certain way. There we go. If it succeeds, we go down here to the success label. So we basically, at that point, totally ignore all of the fail code, right? We're just like branching around. On the other hand, if it fails, then execution falls through because it's not going to jump if R14 is not greater than or equal to 0. So if we fail, maybe I should put this in a red. If we fail, then it's going to fall through to the next label and then the next instructions. Some people like to say, let's jump to the success label, and then if not, let's jump to the fail label. That can buy you a little bit more, I don't know, jump length if you have a giant program. But in this case, I'm just going to let it fall through. It saves us one jump instruction. It's a little more efficient. And so if it fails, then it's going to say, first off, let's print a message that we failed to standard error. If you want a refresher on standard input, standard output, and standard error, see my other videos. And then it's going to print the name of the file that failed. So that's this part right here. It's going to say, hey, we failed to print, or sorry, we failed to open this file name for reading. And then it's going to print a new line there with the CRLF thing. And then it's actually going to exit the program at that point. It's going to say, all right, we failed. And so the whole program just quits. And that's my die function that I showed you earlier. It's just going to call the system call code for quitting, and it's going to give a return code of 1 to indicate to anyone automating our program, including new make, that, well, our program failed. At least it failed. Okay, so we got all that. And then we got the success. And so now you kind of know the idea behind opening a file. Let's do that real fast, just for fun. So file tests. Oh, I know what to do. I'll just comment out these instructions, just so that we're only doing the file open. Yeah, that's pretty good. And then we won't close anything just yet. So now let me run this in the terminal real fast. Make run. It says it successfully opened the file input.txt and then the program exited. No problem. That error code 1, that's because the output file doesn't actually exist. So don't worry about that. And let's change the name of the input file just to show you that it can fail and we can detect it. I'm going to put a 2 there so that the program will try to open an input file that doesn't actually exist, and then I'll run it again. Notice how it says failed to open file input2.txt, and then it says terminating program after failure to open file. And then this time, notice how the make file never got far enough so that it tried to print the MD5 sums of the input and output files. The assembly program just failed, and so GNU make said, I'm not going to proceed any further. Kind of useful when your program gives good exit codes, right? Because then other programs know when to stop, or maybe what to do depending on what's happening. So I'm just going to fix this real fast. Then I'm going to go down here, and maybe the next thing I want to add is closing the files. So we've got a function to open a file for reading, and then we have a function down here that is not implemented yet for closing the files. So I'm going to do, let's see, what is R12? R12 is the input file. So I'm going to close R12. So basically this function, it's going to take one argument. It's just going to take one file handle. So that's why I'm giving the file handle of the input file as the first argument, and then I'm just going to call it. So let's copy paste close file underneath this. So I'm going to do like some more space. And let me go get this from my solution, close file. And it's going to be a pretty simple one. Really nothing much to it. I'm just going to write my C++ prototype saying, well, it takes in one argument and it's a handle. It doesn't return anything. It attempts to close a file, and I'm just going to use R12 to hold the incoming argument. Your programs at home should probably be a little bit better than mine. You should check to see if the file successfully closed or not and respond in some kind of a way. But for me, I'm just saying, I don't really care. I already showed you that we can check for a return value, so I'm allowed to be lazy now and just sort of try to close it and then just assume it all went according to plan. So grabbing the incoming arguments here, that's why I'm using R12. That's why I'm doing a push pop pair. And then the system call code to close is pretty easy. You just say, here's the code to close, stick that in RAX. Let me go up real fast. Notice how sysclose is the call code number 3 on line 43 there. So I send it the call code 3 to say, let's close a file. It only wants one argument, which is just, what is the file handle that you want me to close? Remember before, the operating system created a bunch of stuff under the hood and gave you a file handle. You can then use the file handle to close a file, read a file, write to the file, whatever to the file. So it's pretty easy. Once I've set up the incoming arguments to the system, then I actually use the system call instruction, syscall, and then I can assume it's probably closed at that point. Then a return statement at the end. And now I should be able to run it again, and we shouldn't see like any additional thing happening. It should just be, it said it successfully opened the file, and then it just exited. Okay. Now we're ready to add a little bit more. Let's create a file to write. So this is going to be the same thing basically as opening a file to read, except it's going to be a different call code, and we'll give it initial file permissions rather than a read mode flag. But then we'll just get a file handle in return. And I've also stuck this into another function, of course. So the file name to write, line 109, if you just scroll up real fast here, or if I scroll up real fast, it's line 27 here, just output.txt. And then the file permissions that we want to use, I'm going to scroll up here. That's the second argument to the system call code. That's just this stuff that I talked about a little while ago, where it's like, we want the user to be able to read and write to the file. We want people in the same group to be able to read only, and we want everyone else to not be able to do anything. Basic Linux permissions, not a big deal. At the end, you should probably maybe note that, this Q, I think I might have said this before, this Q just means quad word, and these zeros are always going to be the same. So really it's just like 3 numbers representing file permissions. I'll go over that in more detail in some other video eventually. So for now, we know that we're going to open a file for writing. Doesn't have to exist yet. We'll give it some default permissions, and those are the incoming arguments to the function that we're going to call now, called create file. When that function comes back, assuming it didn't decide to exit the program because we failed to open the file, we will receive the file handle in RAX per usual, and so I'm just going to stash that away real fast into R13. Remember, R12 has the handle to the input file. R13 has the handle to the output file. And then, for me personally, I put that in comments to help myself remember what I'm even doing, because things can get confusing really, really fast. And while we're at it, before we even write the create file function, I might as well just uncomment these things at the bottom, just to say, let's close both files properly. You always want to do that. So now let's copy paste the create file function. Let's see, I didn't do that already, right? Yeah, okay. So let's do that maybe like right here. I'm going to go grab it from my solution real fast. Create file. Okay, about as complicated as opening a file, just because I put in some checking logic to see if it successfully opened the file, which is a good idea. So here's my function, create file. Takes in 2 arguments. Oh shoot, file creation hand. Let's see, am I using R13? Yeah, oh, I mislabeled that. Instead of saying flags, it should be permissions. So let me just do perms here. Long perms, file creation perms, Perm. I wish I could get a perm, if you know what I mean. Anyway, so, we just have like the file name that comes in and the permissions that come in, and it's going to return a handle just like we did with the read file for opening function, but this time we're going to do something slightly different. So the system call is going to be the code for creating a file. sys create, which is not real unless you define it. So if we just look up, I define that as, where is it? Create, 85. So like right here. Code 85 for system create. Again, not a smart idea to hard code numbers. Defines are way better. So then the first argument that it wants is the name of the file. That's the incoming argument that I took into R12. It has to be a null terminated string. It's going to be output.txt. Then the second argument is the file's permissions. So that's R13 that I took here from the second argument, long perms. Once I've set up those things, I can do the system call right away. The system, again, will try to open the file. It'll try to create the file, set up some data structures under the hood. If it succeeds, it'll give me a valid file handle in REX, the return register. If not, then things have failed and I need to respond to that. So I'm just going to stash the file handle in R14 right away. That's why I'm also preserving R14 in the push pop pair that I have, R14 up at the top and the bottom. So now we got to check whether or not we successfully created the file. Again, same logic as just opening a file for reading. I'm going to compare R14 to 0. If it's greater than 0, I'm going to assume it's a valid file handle. So jump if it's greater than or equal to that label, create file success. I'm still using my appending naming convention. So the name of the function is create file. So that means the success area is create file and then append underscore success. And so then I'm just going to, print a cute message saying, hey, we successfully created the file. Yay. Same thing that we looked at before, basically. And then I'm going to return the file handle in REX. If we fail, same thing that we did before when we were opening a read file. I'm just going to complain, basically, to the user, and then call on my little die function to properly exit the assembly program with a exit code of 1. And I could enhance that to exit with different codes, like maybe exit code 1 means the read file didn't work, and exit code 2 means the write file didn't work, and exit code 3 means we failed for some reason while we were copying the data, whatever you want. I'm keeping it kind of simple. So we got all that. Again, this is not different than reading, just, the call codes pretty much, and, the arguments, but the idea is the same. So now we're ready to uncomment. I think we actually already did that. We're ready to let the program try to create the file. And the only thing we need to add after that is the copying portion and the successful message. So let's see if this works. Do clear and make run. So you can see that the program starts running here. And then it says, okay, the module started. And then it says, we successfully opened the read file. And then we successfully created the output file. Notice how the make file doesn't fail when it tries to call the MD5 checksum of the output file, because now it actually exists. If we list the program, list the directory here, you'll see that the out file has actually been created. It just has a length of 0 because there's nothing inside of it. Notice also that the permissions match what we intended. The initial user can read and write, or the owning user can read and write. The group can only read, and everybody else can do nothing. To heck with you. We can change that real fast just to show you. I can get this R to turn into an RW just by modifying permissions up here. Giving permissions to a group just is a nice way of allowing multiple users to have a shared file location. Add them all to the same group and then set that group onto the file and then set the group permissions to allow people to do whatever you want them to do, read and write or whatever. So let's see, where are the perms? I'm going to change this 4 to a 6. So now the group people should be able to read and write. I can't remember if this will work because the file already exists. Let me give it a try. Okay, I ran it one more time and it looks like it did not create the file because it already existed. So let me just remove output.txt. There should be another system call code you could use to just check to see if a file exists. Or if you wanted to be kind of hacky, you could just try to open the file and see if it succeeded and then close it right away. I wonder if there is a call code for just exists only. I don't remember off the top of my head. So I'm going to remove it and then run the program again. And then we should see now, yeah, now that the file didn't exist and was newly created, now those new permissions that we added are reflected. So the group, anybody who's on the group can read and write, and obviously the group is just the same as my user by default. But again, you could be more complicated than that if you were running a multi-user system and you wanted to share folders or whatever. Okay, so I'm going to remove output real fast, and I'm just going to revert the permissions to 640 so that the group really can't do very much except just read it. And then if I, oh shoot, ls, okay, yeah. So now you can see it reverted. Okay, so we got the out file. I'm starting to get lost here. What am I doing? I'm supposed to copy the data, I think. So file tests, and we are copying the file. I think I just uncommented that. Really? Oh, no, no, no. I'm looking at my solution repo. Okay. That's what I'm doing wrong. So we'll look into your repo or your code. We will uncomment the copy file. I was like, what? How did that program run if I already uncommented that? And we'll uncomment this message for now. Nah, let's leave it until we actually finish everything. So now we got to do the copy file function. So where's that at? Okay, I'm going to copy paste this whole thing. You know what? This would have been like a 5-hour video if I actually had to type this by hand. I can't even remember how long it took me to write this program. I think it was like an hour because I was doing it from scratch off the top of my head. So this would be a nightmare to type, I think, on video, even if I kind of already know how to do it now. So let's see, string length, print null terminated string. This is close file. This is create file. Okay, so I'm just going to do copy file is going to be right before close file and right after create file. Okay, so copy file. Notice the signature that I've chosen for this one. It doesn't return anything. So that's like not great design. You know, I need to check to see if the copying operations inside of my loop actually succeeded and maybe return something to indicate success or failure, or at least exit the program, but I'm not doing that right now. I'm just keeping it a little bit more simple. It takes 2 arguments. The first thing is the input handle, and the second thing is the output handle. Conveniently, we have both of those now at this point. And then here's my register usage. I'm using R12 through R15 to just sort of grab the incoming arguments here for R12 and 13. And then R14 grabs the beginning of the temporary buffer, which I'm going to make on the stack because I think I'm so cool, instead of making it as a global in the BSS section. And then R15 is going to hold the result from the copy operation, or I guess the write operation, so that we can, sorry, the read operation only. Oh, I think I'm only checking the read bytes instead of the read and the write bytes. I'll talk about that in a second. So I could upgrade my program a little bit more if I wanted to, but basically R15 is going to be my temporary variable that looks at the return value to say, hey, did we read anything? Like, how much did we read? So copy file. This is not a video about making local variables, so just trust me on this. I'm going to save the base pointer so that I can use it to save the location of the stack pointer. Then I'm going to make a copy buffer on the stack just by subtracting the stack pointer, because the stack grows downward in memory location numbers. And then the base pointer is going to help me remember where the stack was when I started. I'm just going to say that that's going to be the first byte in my buffer. And I'm going to move that into R14. And let's see, what did I do? Make a buffer on the stack. Oh, did I write like a good program or a bad program? I feel like I should have actually saved the base pointer and not the stack pointer there. Let me see if this runs. If it does run, I probably have a naughty program that might self-corrupt sometimes. And it might be a good idea to move the base pointer as the first, because this is not a stack video, but basically the stack grows downward. So if you subtract from the stack, that means you're sort of like extending its reach. You're allocating like a free space. If I take where the stack... Nope, I got it right. I'm sorry. If I take where the stack ends up after I extend it, then I have a lower address, right? Because it grows downward in memory. If I then say that the new tip where it grew, not where it grew from, but where it grew to, if I say that's the first byte in a buffer, then when you're actually using the buffer, you increase memory locations as you're filling up a buffer. So then that's going to grow back towards where the stack started. So it should be fine. I think if I did go ahead and reversed this, if I used RBP instead of RSP there, then I think I would be going in the wrong direction and just corrupting memory. So just so you know, this is not a stack video, but just so you know. So here's a little label. Again, I'm just kind of suffixing. I'm saying, let's copy the file, and here's like an iteration label. And at the bottom, I'm just kind of jumping back up to that label. So this is a loop. You can imagine this is a while loop. Maybe I should draw that for fun. I got to find more excuses to use my draw pad. So this is kind of like a while loop. I'll say while true, maybe. And here's like the body, and then here's like maybe the end of the body. And so this jump statement just kind of goes back up to the top of the while loop. Hello, green. Okay. This thing's going to frustrate me. So the first thing that happens is we read a portion of the input file into the buffer. So what are we doing? We're just using another system call. We're saying, let's use the call code for read. I can't remember what that was. It might have been, whoops. Oh, I cleared the dang drawing. Oh, hang on. I have undo, I think. Wait. I have that, and then I have undo now. Nope. Okay, I'm not going to mess with it because this will actually terminate my whole program. One of these keys, I forgot which one, will just kill the whole annotator. So if we go up to sys read in the defines, you can see that it is just call code 0. So that means I'm telling the system I would like to read something. First argument it wants is a file descriptor for the input file. In a different video, I showed you how to use exactly this sort of thing to read standard input from the user or from another program that launched your program. But in this case, R12, it's not going to be the file handle 0 for standard input. It's going to be the actual file handle of the file that you're trying to read from, whatever that may have been, whatever the OS gave you. And then here's the address of where to store our characters. And if you look up again, we decided to remember where the first byte in our buffer on the stack was, or you can imagine this is like a local array, like, oh shoot, let's do it again. Let's do more drawings. You have like a function, right, in C, and then here it's like we declared a local variable, maybe not int, maybe a character array. We'll call it A, or how about B for buffer? And then we just gave it, you know, let's say 8 bytes or something for the buffer. I think I still have it set to 2 bytes. Obviously, you want to use more bytes for efficiency, but just to prove that the loop actually works, I'm keeping it small, like I said before. Whoa, what's all that? You see that? It's like smearing. Okay, that's not good. So anyway, we remembered where the buffer starts, and it's going to be R14, and then the copy buffer length is being, you know, used here, and I think I have that set up to 2 still, right? So basically we're saying we want to read from the input file, and we want to read into our temporary buffer, and we want to read at most this many characters, and then we say system call, and it does all the work for us to read that many characters. And then we want to remember how many bytes were actually read, because that could be different from the number of bytes we requested. Maybe we're at the end of the file. Maybe the system is having like some kind of a buffer issue or something. So we just want to remember how many bytes we read, and I'm going to stick that in R15 per this little token up there to remind myself the temporary bytes read should go there. Notice also that when we created the stack, this is not a stack video again, but like I made the stack buffer equal to the length of the buffer that I actually wanted to use. So I used the same symbol, copy buffer length and copy buffer length. So then it's going to try to figure out, okay, how many bytes did we actually read? Let me do that while loop thing again, because I'm feeling it. I'm feeling it. Did I really have to write the word true, especially my bad penmanship? So we're doing while true, and then I'll just say like read, you know, do some kind of a call to read. Maybe we'll say n equals read, like a long, you know, the R15 register is like the number of bytes that we actually read. And then we do a comparison here. So we're saying, you know, if, you know, n is, if it's equal to 0, then we're going to jump to the position in the while loop where we're done, which is actually past the while loop. If you scroll down, you'll kind of see it. So I'm just going to say break. So basically, if we read 0 bytes, then we're done reading bytes. We're just finished. So we just break the while loop, and that's what's going to happen here when we say, let's jump green. Let's jump past the end of the body, and you'll see that in a second. So then, otherwise, if we're not done, that means execution is not going to jump. It's going to just fall through to the next statement here, and that's going to be another system call code to write to the output file. And it's going to be very similar. We just load it up with the system call code for write. Let me just double check what code that is real fast for you. So I'm going to go system call write, which is code 1. And then we're going to give it the target for output, which is going to be a file handle. So, you know, R13 right here, that's a file handle. That's where we want to write. And then the next argument that it wants is the buffer. And that's going to be R14, which is where we just, what's going on? Green? Green. There we go. I'm having issues. That's the buffer that we just read into, right? So if you look here, R14, green. Oh my gosh, okay. So green. We read from the buffer pointed to by R14, and then we read into the buffer pointed to by R14, and then we are using that same buffer pointed to by R14 in order to grab the characters that we're going to send into the file. And then R15 says how many files, or sorry, how many bytes. Green, I'm having such problems. R15 says how many bytes do you want to write to the file? That should be our return value from before, right? Because we want to read a certain number of bytes from the file and then write exactly that many bytes. If we did more, we would be writing some junk data probably. And if we wrote less, then we would be missing data in the output file that was originally in the input file. So you want to do it exactly. And of course, I'm just doing a system call here, but like I said before, your program should probably be a little bit smarter and check RAX after you write to the file, just to make sure that you know how many bytes were actually written. Like what if you read 100 bytes, but then you wrote 90 bytes only, right? That would be like a bad situation. So you'd want to do some branching logic there so that if you read 100 and you wrote 90, you probably want to backtrack the position of the file by like 10. You know, just to make sure that you can actually get all of the bytes into the output file. And seeking backwards 10, that's just another system call. It's not in this program, but it's not too bad. You just make another system call, give it the right call code, tell it how far back you want to go. No problem. So then, by the time we make it here, we're going to jump back up to the iterate label. Let's see, where's that? Yeah, right there. We're going to jump back up to the iterate label. So basically, this is how the while loop continues looping. So let me clear that real fast. Eventually, when we're out of data to read, you know, that's because if we try to read and we end up with 0 bytes, that means we're done. We'll break the while loop. Then we're going to go down here. Notice how it says copy file done, what I was talking about before, just sort of jumping past the end of the body. So if we are done, we jump to copy file done, and all it does is just restore a bunch of registers for us. And then return to the caller. So copy file, we have that handled now. And if I go back up here, file tests, I guess I feel bad about this. I can uncomment the success message, but we probably should have done more checking on the reads and the writes just to make sure that we actually wrote the correct amount of characters and everything succeeded every time. And if not, we exit the program. And only if everything went well, then we print a successful message. At this point in this program, the way it's written, it could totally fail and it'll still say that it was successful. So just keep that in mind. That's bad for your users. Okay, I think we have everything that we need now. I can probably just run the program and see that it works. Let's see. Clear and make run. Notice now, oh shoot, I didn't even show this to you before. Let me just emphasize this one more time real fast. So I'm gonna comment out the part where we actually copy the file. And I'm gonna remove the output file. Then I'm gonna run the whole program again. Notice how the two MD5 sums are different. So remember before I said that MD5 sums, they're basically fingerprints. They're not actually considered secure in the modern era. I just use them because they're small and fun. If you are interested in security, you probably want to use a modern hashing algorithm. So don't use MD5, but I am, but I am. It's basically saying the fingerprint here of input is different than the fingerprint here of the output, quickly indicating to me that the files are different. So if I list the contents of the directory, obviously that's true because the output file is empty still. But if I uncomment this part here where I'm actually copying the file, then I should see that the fingerprints match. And then if I look at what's inside of the output file, it should match what's inside of the input file. Really fast, let me open up a terminal and I'll just cat the input file. So this is all I added, why hello there, added some stuff. This is definitely more than 2 characters, so we can be sure that our buffer loop is actually working. And so I'm going to do clear and make run. And now the output file, notice how it has a matching file size. It's got 38 bytes in there. Same thing for the input. And then the thumbprints, or the signatures, whatever you want to call it, the hashes, they match exactly, indicating that we probably have 2 identical files. Even with MD5, even though it's old and not considered secure, the chances of 2 files kind of having random differences, not hacked differences, but just like random differences, and having the same fingerprint is like astronomically almost impossible. So if I do cat input, input.txt, that's what's in there like we showed before. And if I cat the output, now it is the same thing. Why hello there, added some stuff for both. I could make this as big as I wanted to, just for fun. Maybe let's do a nano on the input file. I'll just add, I don't even know what I'm doing. I'm just going to type a bunch of stuff. Oh, wait, what is this? Remember that thing that people got taught a long time ago? It was like the quick brown fox jumped over the lazy dog, and this was supposed to be all the letters of the alphabet. There's another one that I just heard about, and I don't remember exactly how it goes. Look it up on the internet. It's pretty cool. I think I need to memorize this and stop using the lazy dog. It was something like, what was Sphinx of Quartz? Hear my vow or something like that. You know what? I'm going to look it up for you right now. I don't want to do the wrong thing. It's really cool. I'll type brown fox and then hear my vow. Oh, Sphinx of Black Quartz, judge my vow. That's what it is. Okay, so I'm going to go back to my little VM here. Sphinx of Black Quartz, judge my... I didn't even write vow correctly. Judge my vow. And I think that has all the letters in the alphabet too. Probably less spaces. I wonder if that's what the internet says. If this is true and it has all the letters of the alphabet, that's going to be awesome. I'm going to memorize that for sure. Sphinx of Black Quartz, judge my vow. Anyway, so I'm just kind of adding stuff into this file. And if I run, let me save that here. I'll do a clear. And then I'll do, I'll cat the input file here and then cat the output file so you can see they're different. Then if I run the program again, let me remove the output file just in case. I can't remember if I'm supposed to remove it manually or if I put that into the program. We'll just try it like this. So now they match, and then if I cat again the output file, notice how it's a perfect copy of the input file. Nice. So I think that's pretty much everything that I wanted to show you. Maybe, well, maybe we can use a more efficient buffer now that it's done. The copy buffer, we could change this to like 8 kilobytes or something. We should end up with the same result. Let me run this just as is and see if it ends up being the same thing without erasing the file first. Yeah, it looks good. Let me remove the output file and then run it one more time. So make run, and then cat the output file. Yeah, okay, so it still works. But, you know, whereas before we were just using a 2-byte buffer, there's like very little chance, except maybe at the end of the file, that we would request more data than the file had. But using the return value of the read operation always told us exactly how much was read by the operating system. On the other hand, if we have a giant buffer, we could request way more bytes than the file could ever have, because that file is way less than 8 kilobytes. So again, we still want to look at the return value to make sure we know how many bytes were actually read, and thus how many bytes should be sent into the write file. So I guess that's everything that I wanted to tell you about reading and writing files using system calls. I hope you've learned a lot of stuff and you enjoyed this video and had a little bit of fun. Thank you so much for watching. I'm going to cut the video. I'll see you, whoops, I'll see you in the next video. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.